Hi, this is Chapter 9, Sections 1 and 2, Significance Tests about a population proportion and a population mean. In this chapter, we're going to focus more on the population parameter and use a sample statistic to try to prove that population parameter wrong. We are going to state what we call the null and alternative hypothesis, which are abbreviated H with a little subscript O or 0 for the null. That's what the population is. And an alternative hypothesis is abbreviated capital H with a subscript A. Again, that's alternative. That's what you're trying to find. That's what you want proof of. Use this statistic to prove it. We're still going to do the plan. We're going to have assumptions and conditions, very similar to the confidence intervals. We're going to do the actual test in the calculator. And of course, in the calculator, it says here one sample t-test. In the calculator, it's just a t-test. And then we're going to do our conclusion based on our results of the test. So, Skittles candies offer rainbow bite-sized pieces in a famous candy shell and a chewy center. They're perfect for on the go, yada yada yada. Skittles claims that the actual percentage of Skittles candies colors are equally distributed. Well, I don't agree with that claim. I love the grape ones, and there always seems to be barely any when I open a bag of Skittles. Open up your bag of Skittles and find the proportion of grape Skittles in your bag. Well, after doing this with 3 classes, we realized that grape was more than enough, and it was green that was lacking in its 20% proportion. If they're equally distributed, we would expect 20% of every single color in the bag, since there are 5 colors in the bag. So let's say that in our sample of Skittles, because I know one of the groups had 4 green Skittles out of 101, which if we do that in our calculator, would help to actually have a calculator here. There we go. If we do that in our calculator, I have 4 divided by 101. I get 0.3039 or 0.04 we'll round to. So our p-hat is approximately 0.04. And the population parameter should be 0.20. Notice that we write that as p for the parameter, not p-hat. Not convinced that Skittles candies are equally distributed, so we'll conduct a hypothesis test. To test Skittles' claim in the following way. First step is to define your parameter. It's very important that you write the parameter in terms of the population. So we have the proportion of grape Skittles, which we're changing to green. And instead of a bag of Skittles, that makes it sound more like the sample. Let's say in all possible bags of Skittles. And then we have to state the null hypothesis and the alternative hypothesis. The null hypothesis for our case is what the parameter says it should be. That H subscript O or 0 should be that P equals 0.20. We don't have to write any more words since we've already written them clearly up here, and in fact, the fewer amounts of times you write the words, the less likely you're going to get it wrong. Statement being tested in a test of significance is called the null hypothesis. The test of the significance is designed to assess the strength of the evidence against the null. Usually the null is a statement of no effect or no difference, that no matter what bag we choose, the proportion of green Skittles should be close enough to 0.20 for us to say that the colors are equally distributed, or for Skittles to claim that. The alternative is what we're trying to have evidence for and how we want to prove the parameter wrong. So in our case, we're saying that the proportion is going to be less than 0.20. The alternative hypothesis is the claim about the population that we're trying to find evidence for. The alternative hypothesis is one-sided in this case because we're only interested in deviations from the null in one direction. Meaning if I were to draw my normal curve right now, since we're doing a test based on the parameter, we're going to be using normal approximations. Right now, the mean in the middle, which is the proportion of your population, 0.20, and we're going to try to figure out where that 0.04 that we just found was 4 out of the 101, we rounded up to approximately 0.04. We're trying to find how far away is this? Is it extreme enough to say that we have evidence against the claim that 20% of the Skittles in the bag should be green? We'll have to check the necessary assumptions and conditions before we are able to actually apply the normal model, just like before. So we'll assume that the bag of Skittles is less than 10% of all Skittles in the world. However, we could also say if we knew that the bag was randomly chosen, if it stated that in the problem, we could say the bag of Skittles was randomly chosen from the population, from all possible bags. We have at least 10 green and 10 not. Well, you're probably thinking, we only had 4. What are you talking about? This, when we check our conditions, technically we haven't really counted our data yet. And so when we check this condition, we're using the proportion from the population, which is 0.20. Sometimes they abbreviate it as P with a subscript O to go along with the HO. So when we check our successes, it's N times that population proportion has to be at least 10. And N times 1 minus that population proportion has to be at least 10. So in our case, we have 101 Skittles, and we're multiplying that by 0.20. So 101 times 0.2, we get 20.2. And 101 times 0.8, we get 80.8, which of course are both greater than 10. Remember that this last part here, we kind of throw it in, but it's very important that you say it. If you don't say that the conditions are met so we can apply the normal model, then you really can't carry on any of the test. So you need to say that you're using the normal model. We're going to do a 1 proportion z-test. Okay, so now we're actually going to go into the calculator. I can get it so it's not glaring on you guys. Here we go. I'll stick it over here. So I'm going to hit stat, go over to test. It's number 5. And the P subscript O, see it's also 0, it's also in your calculator, it's 0.2. And we had 4 green out of 101. And we were looking for the direction that's less than. If you look at your curve and how you wrote your alternative, it's also pointed in that same direction. So that's the direction we're choosing. We're saying that over here on this side is our statistic is less than the parameter. Then you calculate, and here's our results. This first number here is your z-score. That's how far down 0.04 is from 0.20. That's how many standard deviations away it is. The second one is the p-value. It doesn't say that. And notice this is e to the negative 5, which means times 10 to the negative 5. You have to move your decimal back 5 places. This is our actual p hat from the sample, and of course our sample size. So I'm going to record all that information in this do part. You only have to write this formula if you love the formulas and you're going to memorize it. Otherwise, just write this name, 1 prop z test, and forget about doing the formula. If I do a 1 prop z test, I'm going to write that my z is negative 4.03, I'm rounding. My p-value is 0.00003, and my p-hat, once again, it was 4 out of 101, which is approximately 0.04. Don't have to write the sample size. However, I should look at my normal curve. That shaded area down here, which technically if we were to draw it in the calculator, we wouldn't even see it because it's pretty much 0. That's this area right here of a curve that adds up to 1. It's how much of the curve you have. This 0.04 has a z-score of negative 4, 0.03, which we've learned in the past, that is definitely extreme. This is 0.20, this is your parameter. So, if your p-value is low, lower than 0.05, that's our standard measurement, then we're going to end up rejecting that HO. So the next part here with our conclude is you make a decision regarding the null hypothesis. You have two choices. Either you're going to reject the HO, the null, or fail to reject the null. And it all depends on your p-value. If your p-value is low, you can reject the HO. If your p-value is not low, you would fail to reject your HO. And that 0.05 is what we call our significance level. It's just a standard amount that we're comparing our p-value to. I mean, I know because we've gone through in Chapter 2 that 4 standard deviations away from the mean is extreme. Well, where's the cutoff? Now we're saying that this cutoff is actually when your p-value is less than 0.05. So if you look at your normal curve, and if this end down here is 0.05, that means if we were to also cut it off on the other end, 0.05, we're talking about a 90% confidence interval. That 90% in the middle is the acceptable range that we wouldn't reject the null hypothesis. However, if your p-value is lower than 0.05, that's considered extreme. So, since the p-value is low, we will reject the null hypothesis because the p-value is lower than 0.05. We have evidence that, and now we're going to rewrite the alternative in context of the problem, that the proportion of green Skittles is less than 0.20. Now when people are grading your AP exam and they're looking at the conclusion, it has to have what they call a direction, which means you're specifically saying it's lower than or greater than a specific alpha value. It has to have a decision. Are you rejecting your null or failing to reject your null? And then you need to say in context that you have evidence or you don't have evidence for the alternative hypothesis. It's those three components they will look for. If you don't have all three, if you have two of the three, you get a P. If you have one of the three, you get an I. If you have all three, of course, you get the E for essentially correct. Interpreting your p-value. This is the extra part, which would be usually as like a part B, or maybe they'll throw it in there in a multiple choice type question. Basically, we're saying if the null is true, if the true proportion of green Skittles in the bag is 20% or 0.20, then there's a 0% chance of getting the results of this bag that we had. Only 4 out of 101 green Skittles, or 4 green Skittles out of 101. So if the null is true, there is approximately a 0% chance of obtaining a bag of Skittles with 4 green out of 101 Skittles. Now there's more than one way to say this last part that I just wrote in. Basically, you're just describing your sample results in context. There's a lot of information here, things that you've never done before. So that is why I also handed out in class this language of AP statistics. So there's little subscripts of basically statements that you could either memorize or just repeat to yourself and get used to saying it this way. What the p-value means in context, what if the p-value is low, what you do, and if the p-value is not low, what you do. We have our conclusion for a confidence interval, explaining what confidence means. And there's more on the rest of the paper. But that way you get used to writing the way that they are expecting you, the people grading your AP exam, how they're expecting you to write your answer. All right, so significance tests in general, it's a formal way to look at sample data to decide between two competing claims. The sample data give convincing evidence against the null, then we have evidence to support the alternative. The null hypothesis versus the alternative, the null always says there's no difference, that everything is just fine the way the population says it is, that there's no changes. To test the hypothesis, we're going to look for our Z value, and there's actual formula with the symbols plugged in for those of you that love the formula. In terms of a variable Z and the standard normal distribution, if we're looking for the alternative being greater than, we're going to end up shading the upper part of the curve. So we're thinking that the sample statistic is higher than the population claims. If we have the alternative says that P is lower than, then we're thinking that we're not getting enough of something, just like in the green Skittles. The sample statistic is lower than the population parameter claims. And of course, you're only shading the lower end of the curve. These first two are called one-sided tests because you're only interested in one end of the curve. This last one, if you really don't have a clear direction in mind, you're not sure which way to go, and of course you haven't looked at your sample data to decide because that's cheating, it's not equal to. That means it's either going to be greater than or less than. It's just not equal to what the population is claiming, that the parameter is claiming. So When we do this in the calculator, if we choose the not equal to, will automatically multiply your p-value by 2. We're still comparing it to the same alpha level, but this is called your two-sided test. So the null hypothesis and the alternative should always be written in terms of the population parameters. Make sure you read the problem carefully, because the problem for our situation is going to tell us which direction to use. Out in the real world, you'll have to decide. But for our situation, we're going to know. P-value, this is just going through what the p-value means in context again. That if the null hypothesis is true, then that p-value is the probability of getting the sample statistic, the sample results. That the test statistic would take a value as extreme or more extreme than that actually observed. It's called, the p-value of the test, or the significance of the test. So, if we flip back real quick, if you have a p-value that is lower than alpha equal to 0.05, then you are able to say the results, sample results, are statistically significant, if you want to sound fancy when you throw in your conclusion. Statistically significant means you found a p-value from a sample result that's small and shouldn't have happened. Probability of that sample occurring is very, very small. If we look at the last page, we have a couple minutes before the bell here. The p-value is just the significance level, that's the alpha. It's just giving us one final step to assess the evidence against the null. We're comparing the p-value to it. We write it as alpha, the Greek letter. If we choose alpha equal to 0.05, we're requiring the data give evidence against the null so strong it would happen no more than 5% of the time. So sometimes they'll reword what the p-value means or your significance level means in multiple choice questions. So that's another way that they could possibly write it, that it shouldn't happen more than 5% of the time. If we choose alpha equal to 0.01, we're insisting on stronger evidence because your p-value now has to be smaller than 0.01. So with alpha equal to 0.01, now the p-value has to be smaller than 0.01. This is how they manipulate statistics out in the real world. If they wanted something definitely to reject the null hypothesis, then they could use an alpha equal to 0.10. That means p-value just has to be less than 0.10 to reject the null. If the problem doesn't give you an alpha level, the standard one to use is 0.05. Here's that statistical significance again, your conclusion, which ways to say it, and here's more importantly the words of caution. You should never write that you accept the null hypothesis. If you don't have evidence, enough evidence to reject your null, oops, there's the bell, then all you're saying is you don't have enough evidence to say that the alternative is true. You either have enough evidence to say it's true or you don't have enough evidence to say it's true. And we'll have to continue next time. I'll finish up with confidence intervals, two-sided tests, comparing them, and look at those book problems.